All right. So we have a couple case studies for you, and we're going to figure out how to select your image sensor. So first of all, I wanted to talk about what does an image sensor do? So there's a couple of basic parts. There is your shutter, there's your pixel array, and then there's your analog front end. So you got your happy sun there. It's sending out all these photons, and they're getting, when the camera shutter opens, they enter and they fill up the pixel, these pixels that have these photon wells that store photons. The photodiode then converts the photons into electrons, and they're read out by some readout circuitry into this analog front end where they're converted from analog to digital. So there's a couple different parts. The analog amplifier applies gain, fixes vignetting. Then it goes through the ADC, and then there's a lookup table that corrects nonlinearities and defective pixels. And then it outputs a raw image. So you're going all the way from photons to your raw image. And so if you ever picked out an image sensor, you know there's so many different specifications. It can get pretty overwhelming. These are some common ones that you are going to have to look at. I just realized there's an error on this slide. The first, so shutter speed and type. Rolling shutter actually should be global shutter, and global shutter should be rolling shutter, so switch those around. But basically, you got your pixel array here, and so your exposure starts and stops, and then in a global shutter, it reads the lines, so it stops, and then one by one, it reads the lines out after the shutter stops. So there's some memory circuitry as well that saves the pixel values before reading the lines out. In a rolling shutter, exposure starts, and then stops, and then reads out all at once. So all the pixels, so the first pixel does an exposure and reads out, second pixel, exposure, read out. So there's a couple different differences in how these images show up. You're all familiar with resolution. That's how many pixels there are, basically. There can be larger or smaller pixels, however. Then there's color filter arrays. So the most common still is the Bayer color filter array. That's because the Bayer demosaicing algorithm is still one of the most efficient algorithms for this, but there are a variety of different experimental filters that are also used. And then there's this signal-to-noise ratio, SNR, and dynamic range, and these are related. So signal-to-noise ratio, so dynamic range, you see this picture has some really bright areas and some really dark areas, and nothing is overexposed and nothing is underexposed. So it has a high dynamic range. And this is related to your pixel size because a larger pixel can actually capture more photons before the shutter closes and it's read out. If it's capturing so many photons that it's bleeding over into the nearby pixels, that's when you get these oversaturation parts of the image. Or if it's not capturing enough pixels, it's going to be a dark area, an underexposed area. And so your quantum efficiency is how many of the incident photons around it's able to convert into electrons. So a higher quantum efficiency is good. So these SNR, dynamic range, and quantum efficiency are all related.